you have many examples. All of you know about sulfuric acid, phosphoric acid, and nitric acid. So, let us today learn how to name oxyacids or how to get the formula of oxyacids. Look here, ortho is an optional term. Ortho. If I say ortho nitric acid, I just mean nitric acid. So, ortho, you can say, you can avoid the term, it is quite optional. Ortho dash dash ic acid. Ic, the emphasis is on ic, sulfuric, nitric, phosphoric, etc. Look here, HNO3 is nitric acid. All of you know this. HNO3 is nitric acid. H3PO4 is phosphoric acid. H2SO4 is sulfuric acid. And HClO3 is chloric acid. Once again, nitric, the emphasis is on ic. Phosphoric, once again ic. Sulfuric, chloric. If you just learn these four names, in a few minutes from now, you will learn nearly 70 acids. The formula of 70 acids with just using this as a reference point. For example, this could also be called orthonitric acid. So, you may be thinking that the formula of orthophosphoric acid is different from phosphoric acid, but it is not so. Ortho is only an optional term. You can say it is like a Mr. something like that. Mr. Mrs. a respectable word. So, orthonitric, nitric, orthophosphoric, phosphoric, one and the same. Now, us acid. Us means one oxygen less than ic. I repeat, us means one oxygen less than ic. It is HNO2, nitrous acid. H3PO3, phosphorus acid. H2SO3, sulfurous acid. HClO2, chlorous acid. Look here, nitric, nitrous, phosphoric, phosphorus, sulfuric, sulfurous, chloric, chlorous. So, these three acids, all of you know from the beginning. There could be slight confusion just regarding chloric acid. So, you learn this little carefully. Chloric acid is HClO3 and it is chlorous, chloric, chlorous. So, what do you mean by us? One oxygen less than ic. And one more oxygen less, it is called hypo dash dash us acid. So, ic, us, hypo, us. What should you put in this blank? Niter for nitric, phosphor for phosphoric, sulfur for sulfuric, and chlor for chloric. So, you remove one more oxygen, HNO, H3PO2. And of course, this hyposulfurous acid, strictly speaking, doesn't exist. And HClO, HClO. Repeat the three names together. Nitric, nitrous, hyponitrous. Phosphoric, phosphorus, hypophosphorus. Spell them, pronounce them clearly. Hypophosphorus. The three parts of the word should be pronounced properly to understand the name of the compound. This one is hypochlorous acid. And HNO, of course, exists as a dimer, HNO twice. So, the formula of hyponitrous acid is just not HNO, it is HNO twice, that is H2 and 2O2, the formula of hyponitrous acid. So, just observe the relation. Nitric, one oxygen less is us, one more oxygen less is hypo us. Hypo in fact means less. Hyper, the opposite, means more. Hyper means more. Hyper means a little too many. A little too many, and it can be called even per, just permanganate, too many oxygens. Okay. So, we will come back to this later. So, phosphoric, phosphorus, hypophosphorus, sulfuric, sulfurous, hyposulfurous. chloric chlorus hypochlorous. You have already learned nearly 3 into 4, 12 acids minus 1 of course. And what is it we are doing mathematically? 3, 2, 1, 4, 3, 2, 4, 3 something. So what should you do? One step above, add one oxygen to get HNO4, H3PO5, H2SO5 and HClO4. So you can see HNO4 is too many oxygens, therefore we call it per or peroxy-ic, peroxy-ic acid. So this is per nitric acid, per phosphoric acid, per sulfuric acid, per chloric acid, and this one is of course per only, per only. What does it mean? All others can be called per or even peroxy. You can call this peroxy nitric acid, you can call this peroxy phosphoric acid, you can call this peroxy sulfuric acid, but that one is not a peroxy acid. How do we know it is not a peroxy? I will explain to you a little later. And why these are peroxy and why that is not peroxy, anytime we could know that. So let me give all 4 names together: pernitric, nitric, nitrous, hyponitrous; perphosphoric, phosphoric, phosphorus, hypophosphorus. So now you nearly have 15 acids and their names, and the gradation, it is 3, 2, 1. You are decrementing one oxygen, removing one oxygen after the other. In this particular case, you give one more oxygen. Now, so far so good. We have learnt. So what is the emphasis on? You start with ic, ic. One oxygen less is us. One more oxygen less is hypo-us. And one oxygen more is per or peroxy. Per or peroxy -- ic acid. I hope you got my point. So 4 prefixes and suffixes, and I can easily tell you same will be the formula for if phosphoric acid is H3PO4, arsenic acid will be H3ASO4. You know nitrogen, phosphorus, arsenic, antimony belong to the same group. So whatever be the formula of phosphoric acid will be the same for arsenic acid. You may get a doubt, why not we imitate HNO3? Nitric acid is only H, but the other one is H3H3. So antimonic acid, if you want H3SbO4, it is beyond the scope of your particular exam, but still you look at the underlying principle. Phosphorus, arsenic, antimony, they all of them have the same formula, and most importantly arsenic and antimony, they are not imitating nitrogen. What does it tell you? The behavior of first and last in a particular group, nitrogen, bismuth, the behavior of nitrogen and bismuth differ from the rest. There are 5 members in a family, the youngest and the oldest. The behavior of the youngest and the oldest differ. Obviously, the young one is too young and the old one is too old. This fellow is too small, he can't form many bonds, and this fellow is not interested in forming bonds, which is called inert pair effect, which we learn in some other topic. So what is the emphasis on? The formula of arsenic acid is similar to that of phosphoric acid. Phosphorus, arsenic, antimony, they have similar behavior, and nitrogen and bismuth are slightly different from the rest in the sense that nitrogen is too small, it just have 2s and 2p orbitals, it can't have more than 3 or 4 bonds, and bismuth is too big, it doesn't want to form many bonds. Nitrogen can't form NCl5 because it doesn't have vacant orbitals. Bismuth doesn't form BiCl5 because it doesn't want to form, inert pair effect. Bismuth doesn't want to combine with 5 species. So similarly you have the acids of phosphorus, arsenic, antimony here, sulfur, selenium, tellurium here. So chlorine, bromine, iodine. So what will be the formula of periodic acid? Periodic acid, which is mistook as periodic acid. It is not periodic, it is periodic, just as perchloric. So it is HiO4, HClO4, HiO4. What will be the formula of bromous acid? Bromous, You just have to tell me bromous similar to chlorus, HBrO2. Remove chlorine, put bromine, you will get bromous. Iodus, hypoiodous acid, HIO. Hypochlorous acid is HClO, hypoiodous acid is HIO. I hope you got what I mean to tell you. So it's not just the formula of these just 15 acids. You have so many other acids of arsenic, antimony and selenium, tellurium, bromine, iodine. All of them put together you have already learned some 30 names. Let me revise quickly. What will be the formula of selenic acid? First of all, you should know who is selenium. Oxygen, sulfur, selenium, tellurium, polonium. They belong to the same group, and the formula of sulfuric acid is H2SO4 and that of selenic acid will be H2SeO4. Look at the minute difference. Here it is sulfur S, here this one is selenium Se. Telluric acid H2TeO4. So any number of acids you can derive from the same prefixes and suffixes using the same principle. And now, what do you mean by pyro? Pyro means acid plus acid minus H2O. Which acid? Whatever be the acid in question. Suppose you want the formula of pyrophosphoric acid. Pyrophosphoric acid. What did I say about pyro? Pyro means you have to take two acid molecules and remove water. What is phosphoric acid? H3PO4 plus H3PO4 again minus H2O. You will get, if your arithmetic is right, H4P2O7. What is the formula of pyrophosphoric acid? Don't try to mug it up. You just learn the meaning of pyro. Pyre means fire. Pyre means fire, and you are heating an acid and the water will be liberated. Pyre. Pyrophosphoric acid, acid plus acid minus H2O. You have H3PO4 plus H3PO4 minus H2O, H4P2O7. And same is the case with pyrosulfuric acid. Put your mind on that. H2SO4 plus H2SO4 minus H2O. I am not doing all the homework for you. Homework means it is supposed to be done by you. Pyrosulfuric acid, H2SO4 plus H2SO4 minus H2O. You get at the end of the day H2S2O7. You got my point. So, what is that you should learn? Not the formulae, the meaning of the particular prefix or suffix. What do you mean by pyro? What do you mean by artho? What do you mean by hypo? Like that. Now, we have seen 5 or 6 prefixes, suffixes, and now let us move to meta. Meta means just acid minus H2O. Which acid? Whatever be the acid in question. Metaphosphoric acid. Metaphosphoric acid. It is H3PO4 phosphoric acid. Meta means minus H2O. Meta means minus H2O. Meta something, something minus H2O. Meta this minus H2O. Metaphosphoric acid minus H2O. HPO3, metaphosphoric acid. Alright, lastly, you have another prefix, thio. Thio means sulfur in place of oxygen. You will come across this at many places, sulfur in place of oxygen. For example, thiosulfuric acid. Thiosulfuric acid. How would you write the structure? Thiosulfuric acid. Formula H2SO4 sulfuric minus O plus S. What is it I have been telling you? Sulfur in place of oxygen. You have to remove an oxygen and add one sulfur. Put sulfur in its own place. So H2SO4 minus O plus S, you will get H2S2O3. Interestingly, the formula of thiosulfuric acid is, the formula of the structure of sulfuric acid looks like this. SOHOH. Yesterday we discussed structures at length. H2SO4, H2SO4, number of OH groups is equal to number of hydrogens present. This we did in the last class. Since I have 2 hydrogens, I am putting 2 OH here and 2 double bond O's. So it is H2SO4. So thio means oxygen should be replaced by sulfur, H2S2O3. This is sulfuric acid. Which oxygen you will replace? At least you go by a blind rule. If you have 2 hydrogens, you should have 2 OH groups. I told you that except with these three, H3PO3, H3PO2, with all others, the number of hydrogens is equal to number of OH. Did we discuss that or not yesterday? H2SO4, 2 hydrogens, 2 OH. So you stand by that. H2S2O3, there are 2 hydrogens, and you continue with 2 OH groups. And where should you put sulfur? This is where sulfur, S double bond S. So you might as well get a question, which of the following has SS bond? Yes, this thiosulfuric acid has got an SS bond in it, SS bond. Okay? So you have learned the names. Let me quickly revise what we have learned. Ik, us. What do you mean by us? Recollect for yourself. Us means 1 oxygen less. And hypous, 1 more oxygen less. This is the reference point. We start here. This is our starting point, and from there on we proceed by removing oxygens, and you add 1 oxygen, you get per or peroxy. Per or peroxy. We discuss peroxy substances in the next class at length, but let me give you briefly what I mean by peroxy. H2SO5. While finding the oxidation states, you just give -2 to oxygen, -10, 2 hydrogens +2, sulfur gets +8. So, by giving -2 to oxygen, I repeat, by giving -2 to oxygen, if the other atom gets higher than the group number, then it is a peroxide. Of course, there is a hitch to this rule which we will discuss later. But as of today, how to find whether it is a peroxy acid or not? You just give, and this +8 is impossible for sulfur. Sulfur belongs to 6A of the periodic table. Sulfur, the maximum oxidation state could be +6 only. We will discuss oxidation states in the next class. So, for the time being, sulfur cannot entertain an oxidation state of +8. Therefore, we say H2SO5 is peroxy. HClO4, regarding HClO4, -8 +1 +7, and chlorine can easily handle an oxidation state of +8. Chlorine belongs to 7th group, its maximum is +7, minimum being -1. So, the minimum maximum rule we will discuss in the next class. Today we just are confined with the names of oxyacids. Perhaps in the next class we go at length in detail about oxidation states. Next class will definitely be about oxidation states only. So, per or peroxy, 1 oxygen more, 1 oxygen less, 1 more oxygen less, and pyro means acid plus acid minus H2O, meta means acid minus H2O. So, you should be noting down like this: 1 oxygen less, 1 more oxygen less, acid plus acid minus H2O, acid minus H2O, 1 oxygen more. So, let me take H3PO4, H3PO4, H3PO3, 1 oxygen less, 1 more oxygen less, H3PO2, 1 oxygen more, H3PO5, acid plus acid minus H2O, H3PO4 plus H3PO4 minus H2O, meta, 1 acid minus H2O. So, phosphoric, 1 oxygen less is us means 1 oxygen less, hypoos means 1 more oxygen less, per means this, meta, pyro. So, that is all about the names of oxyacids. And how to draw the structure of oxyacid, yesterday we discussed H4P2O7. If you have 2 phosphorus, draw 2 phosphorus, and 4 OH, 4H means 4 OH, distribute equally, OH, 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 and you have 3 more oxygens, 1, 2, 3, a double bond, a double bond. So, you know oxygen forms 2 bonds, and that was yesterday's lesson. And how will you draw the structure of H2S2O5, an interesting acid, H2S2O5? I know all of you would prefer to draw the structure like this: 2 sulfurs, 2 OH groups, 5 oxygens, 1, 2, distribute equally. Oxygen forms 2 bonds, this one is. Why not this is correct? This is wrong. This is wrong. You have to tell me why this is wrong. Both the sulfurs have lone pairs, and lone pairs you know cause repulsion. That was our last lesson. Lone pairs disturb the other bond pairs. So, we will try to amend the structure like this: S, OH, double bond O, S, double bond OH. And what's the idea? Look here. Here both the sulfurs have lone pairs. Here at least one sulfur is saved from the lone pair. I repeat, at least one sulfur is saved from the lone pair. Okay, because this lone pair is avoided by putting one of the oxygens here itself. So this sulfur has 6 bonds, this sulfur has 4 bonds. So this is the correct structure and this is wrong. You may as well get a doubt, why not we put this oxygen also here so that all of them are avoided. S double bond O, OH, S double bond O. What is it I am trying to do? This oxygen I am making like this. Okay, this is wrong because this is wrong. This may be possible in few molecules, but this is generally wrong because here hydrogen is offered the 6th bond, 1, 2, 3, 4, 5, 6. Sulfur has many pairs of electrons, 3s2, 3px2, 3py1, 3pz1. For sulfur to form 6 bonds, this pair has to be excited and this pair also has to be excited, which is rather difficult. Difficult for hydrogen. Sixth bond is not offered for hydrogen. Of course, sulfur forms 6 bonds with sulfur, I mean fluorine, SF6. So 6 unpaired electrons are offered to fluorine, a very highly electronegative element, but not to a poor hydrogen, which is not that highly electronegative. So hydrogen cannot break the pairs of electrons. When fluorine comes here, when fluorine approaches sulfur, the pairs of electrons automatically get separated because fluorine is highly electronegative. It repels the pairs of electrons and they get separated automatically. Hydrogen doesn't have the same kind of knack in terms of electronegativity. Right. This is a little too high for your discussion, not necessary. I just want to explain what's happening. Now, another procedure, a simple procedure which will answer hundreds of questions, that is hydrolysis. Hydrolysis, you just break the bond, H on one side, OH on the other. H means H plus, OH means OH minus. Hydrolysis, and H plus will obviously go to the more electronegative, whoever is more electronegative. Who is more electronegative? Fluorine greater than, oxygen greater than, nitrogen greater than, chlorine greater than, hydrogen greater than boron. You should always remember this order. There is no choice for you. FONCl greater than, H greater than B, something like that. OH minus goes to whoever is more electropositive. And use any number of H plus OH minus depending on their valency. Use any number of H plus OH minus depending on their valency. So more electronegative, fluorine, oxygen, nitrogen, chlorine, hydrogen, boron. Fluorine, oxygen, nitrogen, chlorine, hydrogen, boron. More electronegative, more electropositive. Now, for example, if you start hydrolyzing BCl3, break the bond, 3H, 3OH. Why am I taking H there? Because chlorine is more electronegative, H plus. I will show it to you more clearly. It is BCl, Cl, Cl. I am breaking a boron chlorine bond with water. Hydrolysis means breaking a molecule with the help of water. You can apply the same definition in so many places. Electrolysis means breaking a molecule with the help of electricity. Pyrolysis means breaking a molecule with the help of heat. Pyre means fire. Pyre means fire, as I already told you. So, break the bond, H plus here, OH minus here. Chlorine is far high electronegative than boron. You do the same with this, HOH, HOH. What is it you are end up getting? BOH thrice, HCl, HCl, HCl. So, BCl3 on hydrolysis. Break the bond, 3 hydrogens collectively, 3 OH. I would as well want to write H plus here, but that's a waste of time. H plus, OH minus. So, 3 H plus, 3 OH minus. You will be end up getting BOH thrice. It is none other than boric acid, H3BO3. So, how are oxyacids prepared? By the hydrolysis of halides, BCl3. Right. Then, PCl3 on hydrolysis gives, it's anybody's guess, 3H, 3OH, which is nothing but POH thrice, it's H3PO3. What is the name? H3PO4 is phosphoric acid. H3PO4 is ick. H3PO3 is us, phosphorus acid. Okay? So PCl3, BCl3, and now let us carefully electrolyze NCl3. You have to be very, very, very careful. This is a very, very, very good example. Break the bond, H plus on one side, as I told you, OH minus on the other. Where will H plus go? Goes to the electronegative. OH minus goes to electropositive. And which is more electronegative, which is more electropositive? We already have FONCl. I told you nitrogen is more electronegative than chlorine. So you write 3 hydrogens here, 3 OH here. So you have NH3 plus HOCl. You know the significance of this reaction? Many people believe that the electronegativity of nitrogen and chlorine are one and the same. According to Pauling scale, they were even given the same ranking, 3, 3. But this reaction, for once and for all, settles all scores. NCl3 on hydrolysis producing NH3 means H plus is attacking nitrogen only because nitrogen is more electronegative. I may not know who is more electronegative, you may not know who is more electronegative, but H plus knows it better. Why is H plus preferentially attacking nitrogen? Why not chlorine? Why is H plus attacking nitrogen? Just because nitrogen is more electronegative. So this reaction settles all the scores regarding which is more electronegative. I hope you understand. So there are several molecules that have to be hydrolyzed. Perhaps you take SCl4, break the bond, 4 hydrogens, 4 OH. You get SOH 4 times. SOH 4 times, this is OH. This is, I am writing in a little hurry. OH, 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 because I want to do too many things in so little time. SOH, OH, OH, OH. So remove the, so SOH 4 times, when you happen to have 4 OH groups on one sulfur, automatic loss of water, you get H2SO3. So how are you supposed to know? Just remember, silicon can handle 4 OH groups. OH groups are electron withdrawing, and the central atom should have sufficient electropositivity to withstand the onslaught of the electronegative elements. So silicon is comfortable even with 4 OH groups, SiOH 4 times, which is called H4SiO4. This is silicic acid or orthosilicic acid for that matter. Phosphorus can handle only 3H. Sulfur can handle only 2. Phosphorus and boron can handle 3 OH. Sulfur only 2. Chlorine, bromine, iodine, carbon, nitrogen, they can handle only 1 OH. So what does it tell you? As the electropositivity increases, the tolerance towards electron withdrawing OH groups is increasing. Silicon is electropositive, for which for silicon even 4 hydroxy groups, okay, not bad. I am electropositive enough. But phosphorus 3, sulfur it's only 2. So what happens if you happen to get more OH groups than the maximum limit? Automatic loss of water. You just see PCl5. PCl5 on hydrolysis gives 5H, 5OH. I here have an occasion to write POH 5 times. So phosphorus, you know, cannot handle 5 OH groups. The maximum is 3. What happens? Automatic loss of water. H2O. You get PO, OH, OH, OH. This once again proves that phosphorus prefers to be tetrahedral rather than trigonal bipyramidal. PO, H3PO4. So you are getting POH 5 times, which is none other than H3PO4 dot H2O. H3PO4 dot H2O. So PCl5 on hydrolysis gives phosphoric acid. So you can handle any number of SiCl4, silicon tetrahalide. SiCl4 on hydrolysis gives 4H, 4OH. You get SiOH 4 times H4SiO4, orthosilicic acid. Now, PCl5 on partial hydrolysis. If the question clearly mentions partial hydrolysis, then only you need to be a little alert. Otherwise, PCl5 and hydrolysis, as I told you, gives H3PO4 only. If the question clearly mentions partial hydrolysis, okay, the answer is POCl3. Once again, tetrahedral. So only 2 chlorines are partially hydrolyzed, and SbCl3, BiCl3, they undergo partial hydrolysis only. Partial hydrolysis only to give SbOCl, BiOCl. And let us not go into the details, because using the procedure you can almost handle many acids. The hydrolysis of many substances you can find out. There are 1 or 2 exceptions, you learn them separately. The best way to learn is learn as many things as possible using a generalization, and if 1 or 2 are against the generalization, you just learn them separately. Be careful. What is that you should be careful about? Partial hydrolysis of PCl5 and hydrolysis of, it is not even, they undergo partial hydrolysis only. There is nothing called hydrolysis here. In the case of BiCl3, SbCl3, let us not go into the reasons. Now is not the time. So, SbCl3, BiCl3, they undergo partial hydrolysis only. So, this will be the answers: TBM, oxychloride, bismuth oxychloride. And the hydrolysis of xenon halides, okay, you have to learn this separately. Xenon fluorides. Hydrolysis of xenon fluorides, it is a little out of the ordinary. I warn you, you learn them separately. So, hydrolysis of xenon halides, and there are certain molecules which do not undergo hydrolysis at all. Do not undergo hydrolysis. For example, a carbon-carbon bond, a carbon-hydrogen bond, they don't undergo hydrolysis. Why? The bond is non-polar. I told you H plus goes to somewhere, OH minus goes to somewhere. Here nobody is plus, nobody is minus. But in the case of boron chloride, at least you can say this chlorine is minus, boron is plus. Therefore, H plus will attack, OH minus will attack here. So, you need some kind of polarity for hydrolysis to take place. So, no hydrolysis for carbon-carbon, carbon-hydrogen bonds, CC-CH bonds, and CCl4 doesn't undergo hydrolysis, and salts of strong acids and strong bases in a different context, they don't undergo hydrolysis. This is salt hydrolysis. What I am teaching you is not salt hydrolysis. It is a simple procedure to predict the product. It is not exactly a shortcut, but this salt hydrolysis is slightly different. So, salts of strong acid, strong, so no hydrolysis for, no hydrolysis, and any bond involving fluorine except with xenon and boron. Any bond involving fluorine, I am not writing it completely, any bond involving fluorine except with xenon and boron, because fluorine bonds are very strong, you can't afford to break them. Okay. Now, XeF2, if we follow the procedure, break the bond, 2H, 2OH, you get XeOH twice, and xenon doesn't handle even 1 OH. Beryllium and xenon, they can't withstand, they withstand only 0 OH. They don't accommodate any OH. So, you get HF, of course, HF, which dissolves glass. Glass gets dissolved. This is called etching of glass. Means glass dissolves in HF, which is called etching of glass. Now, XeO, you get XeO, and that XeO also becomes Xe and plus half O2. So, the hydrolysis of xenon halides do not, xenon fluorides do not follow the generalization. You learn the hydrolysis of xenon fluorides separately. So, partial hydrolysis of PCl5, hydrolysis of SbCl3, BiCl3 and xenon fluorides. You have to learn 4 things separately, and all others you can just blindly follow the generalization. For example, aluminum nitride, in a process called Serpex process, you will get an occasion to hydrolyze this. What will you get? Break the bond. 3OH, 3H, there ends the matter, NH3. So, ammonia is said to be one of the byproducts in Serpex process. That is not necessary, but so Mg3N2 magnesium nitride, break the bond, 6OH, 6H, you will get 2NH3. Of course, magnesium hydroxide, I am not bothered about this, aluminum hydroxide. So, I will point out only the chief product, NH3 in both the cases, ammonia. and calcium cyanamide, CaNCN, calcium cyanamide. Break the bond wherever there is polarity, different. Calcium, nitrogen, nitrogen, carbon, carbon, nitrogen. Wherever there is electronegativity, break it. So you get 3H, 3H again, 2OH, 4OH, ammonia, ammonia. Carbon with 4OH, you all know, carbon cannot handle, okay, automatic loss of water, you get CO2. This CO2 and calcium hydroxide, you end up getting CaCO3, calcium carbonate. Cyanamide process for the manufacture of ammonia. Calcium cyanamide and hydrolysis gives ammonia, ammonia, calcium carbonate. How do you get calcium carbonate? Calcium hydroxide from calcium, carbon and 4 OH groups, which carbon any case can't handle, so CO2. There you are. So, after the hydrolysis, how to get an anhydride? HNO3. What is the anhydride of nitric acid? Just add one more HNO3 and remove water, minus H2O. You get N2O5. N2O5 is the anhydride of, how do you get an anhydride? Remove all hydrogens in the form of water only, comfortably. H2SO4, anhydride, minus H2O. You get SO3. So what do you conclude? SO3 is the anhydride of H2SO4, or SO3 when added to water, you get this. It is A minus B is equal to C, or C plus B is equal to A. Either way, it's the same. So how to get an anhydride? By removing all hydrogens. None of the hydrogens should be seen. For example, if you have H3PO4, you take another H3PO4 and remove water as long as all oxygens do not go away. Minus H2O, minus H2O. Why am I removing so many H2Os? I don't want to see a single hydrogen. All hydrogens have to be removed in the form of water only. What you have to subtract is H2O. And what is the outcome? Hydrogen should not be seen. So you end up getting P2O5. P2O5, which exists as P4O10. P2O5 only exists as P4O10 phosphorus pentoxide. So what is the anhydride of H3PO4? It is straight away P4O10. So what will be the anhydride of HClO4? You have a field day with as many acids as you know. HClO4, HClO4, minus H2O, Cl2O7. You should practice from your end. We can't give you the practice in this session itself. Now let us go to questions. First question, which of the following is not a peroxy acid? Which of the following is not a peroxy acid? What are the options given? Perphosphoric acid. I already told you perphosphoric, pernitric, perdisulfuric, perchloric. What did I tell you about perchloric acid? It is just HClO4. It is not a peroxy. Why? There is no oxygen-oxygen single bond. So to say, there is no need for an oxygen-oxygen single bond. Oxygen-oxygen single bond arises out of some need where the valencies are not clearly satisfied. Here HClO4 can quite comfortably ClOH double bond O, double bond O, double bond O. We discuss more about peroxy substances tomorrow. Let's go to, so what is the answer? Perchloric acid, answer 4. Let us go to second question. Hydrolysis of NCl3 gives NH3. Which of the following is X? What a wonderful question. We just have looked at it. NCl3, break the bond. H3H3OH. So where do you stand? NH3 is one of them, and 3HOCl or HClO, hypochlorous acid. Answer is 3. Okay. So how is ammonia prepared? By the hydrolysis of aluminum nitrate, by the hydrolysis of magnesium nitrate, by the hydrolysis of calcium cyanamide, CaNCN, by the hydrolysis of NCl3. So after all said and done, nitrates and hydrolysis give ammonia, and in this particular question NCl3, you have already got HOCl. Let's go to the third question. Which of the following has SS bond? What a funny question. H2S2O6, H2S2O7, H2S2O8, mustard gas. Which of the following has SS bond? H2S2O6. Draw the structure. 2 sulfurs, 2 OH. This is only yesterday's procedure. We did it quite many times. 2 sulfurs. How do you know 2 OH are there? 2 2 hydrogens. And how many more oxygens? 6 oxygens, which will enable you 4 more oxygens. 1, 2, 3, 4 distribute equally. And now the 6th bond of sulfur. Here you have got the SS bond. So the answer is 1. And you try to draw the structures of H2S2O8. H2S2O8. It is a peroxy acid. Minus 16 plus 2 plus 14. And sulfur is getting plus 7, which is impossible for sulfur. Plus 7 is too high for sulfur. So you will not find an SS bond. Moreover, you will find OO bond. So what about mustard gas? The last question, what about mustard gas? Mustard gas. You should study all the options. CH2, CH2, Cl. There is only one sulfur in mustard gas. It is beta dash dichlorodiethyl thioether. Why is it called thioether? Why is it called thioether? Because oxygen replaced by sulfur. If you have oxygen here, you would have called it an ether. If you have oxygen here, you would have called it an ether. This is a thioether because oxygen has replaced sulfur. So ethyl, diethyl, thioether, beta dash dichloro. This is alpha, this is beta dash dichloro diethyl thioether. That's mustard gas. So there is no sulfur at all. Next question. Compound X is an anhydride of sulfuric acid. So what is the anhydride of sulfuric acid? A moment ago we saw minus H2O, SO3. So what's the question? The number of sigma bonds and pi bonds. Very funny. 1 sulfur, 3 oxygens, 2 bonds each. So 3 sigma, 3 pi. We discussed that in the last class itself. So the answer happens to be 1. Next question. Sulfur trioxide is dissolved in heavy water, SO3 plus D2O. All reactions of D2O and H2O are similar. All chemical reactions, let me repeat. All chemical reactions. SO3 plus H2O, SO3 plus H2O, you get H2SO4. SO3 plus D2O, you will get D2SO4. And what's the question about? The hybridization of sulfur, same as whatever it is, sulfate, SO4, 2 minus. How will you find hybridization? 6 plus 0 plus 2 by 2, 8 by 2, 4, sp3. Okay? So the question is, how does heavy water react with sulfur trioxide? The answer should be similar to that of water. Heavy water is no different. It is of course water. Okay? Just heavy, a little heavy. Okay, if I remove the shirt, I will become normal RSN. With this shirt, heavy RSN. That's all. sp3. Next question. Which of the following is an acid? Calcium hydroxide, as you know well, first option is a base. Ammonium hydroxide again is a base. NaOH is a base. What about POH thrice? It looks like a hydroxide and you will be misled to call it as a base, but it is H3PO3, phosphorus acid. And we got exactly the same when we hydrolyzed PCl3. Remember that? 3H3OH, you get POH thrice, phosphorus acid. So the answer happens to be 2. Next question. Chlorine atom in its third excited state. Very good question. But this happens to be yesterday's. I took some questions for revision also, so that we don't forget what we learnt yesterday. 3s2, 3px2, 3py2, 3pz1. This is the ground state of chlorine. Ground state. First excited state means first excited state 1, 1. This is not ground state. First excited state. So you have 3 unpaired electrons. Chlorine can form 3 bonds like ClF3, etc. 3px2. One more second excited state. So you get 3d1, 3d1. So now in this state, chlorine can form 5 bonds. The question says, chlorine atom in its third excited state reacts with fluorine to form a compound. Third excited state, it will have first 2, 2, 2, 1. What is this? Ground state. First excited state, 2, 2, 1, 1, 1. 3 unpaired 1 unpaired electron, 1 bond, as in the case of Cl. 3 unpaired electrons, 3 bonds, as in the case of ClO2 minus. Second excited state, it will be 2, 1, 1, 1, 1. 5 unpaired electrons, 5 bonds, Cl double bond O, help me, O minus. Third excited means everything. First, second, third. 1, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7 unpaired electrons. Chlorine can form 7 bonds. Which is the molecule in which chlorine is forming 7 bonds? ClF5 pentagonal. That is only 5 bonds. So you have only ClF7. Matter of factly, chlorine doesn't form ClF7, but that is none of our business. The question says that chlorine is reacting with fluorine in its third excited state. Means they are telling you that chlorine is forming 7 bonds, ClF7, and this is pentagonal bipyramidal. Okay, this is a very, very good pentagonal bipyramidal. This is a very good question where you have to use the data given in the question, not your own mind, not your own knowledge whether chlorine forms ClF7 or not. How are we supposed to know whether somebody forms this or somebody doesn't form that? They have clearly given chlorine is reacting in its third excited state with 7 unpaired electrons, as many as 7 unpaired electrons. And next, metaphosphoric acid, straight away question. H3PO4 is phosphoric minus H2O, you end up getting HPO3, which is metaphosphoric acid. Answer is 1. Next, please. Which of the following oxides is an anhydrate of HNO3? You just remove HNO3 plus HNO3 minus H2O. What is that you get? N2O5. So N2O5 is the anhydrate of HNO3. So the option is 3. Correct answer is 3. Next question. Which one of the following is a correct pair? XeF4sp3? No. How do we know? XeF4 is once again a revision question. 8 plus 4 by 2, it's going to be 6 sp3d2. What is that we did? Valence electrons of xenon, 4 fluorines. Second set, XeF2sp? No. XeF2, 8 plus 2 by 2, 5 sp3d. Next, XeF2sp3d, yes, we already got it. So answer is 3. And XeF4sp2, not at all, because we already know. So the question is about XeF4 and XeF2 only. It is enough if you know what is the hybridization of XeF4, XeF2. So 8 plus 2 by 2, 8 plus 4 by 2. For the benefit of some of the late tuners, xenon has 8 valence electrons. 8 plus 2 by 2, 5 sp3d, and 8 plus 4 by 2, 6, which is sp3d2. So valence electrons plus monoval atoms. And thank you for today. We'll continue tomorrow.